Functional coverage closure in SoC interconnect verification with the iterative machine learning. The abstract. The system on chip SoC interconnect connect to various components of the SoC. The ever-increasing SoC design complexity has brought about boosted complexity in SoC interconnect designs that interconnect hundreds of master and slave components with various protocols. Functional verification of such SoC interconnect designs constitute a critical part of the SoC design process. To reach the functional coverage closure, the design verification team expends excessive time and resources running constrained random simulations, analyzing uncovered scenarios, modifying the test and setting in turns. This paper represents a novel and alternative approach that exploits iterative machine learning by adopting a software solution called SimAI. Given the original set of the test and the lengthy list of the target scenarios, the software generates instructions for Xcelium logic simulator to address those target scenarios efficiently. Moreover, by evaluating simulation traces and results, it generates a new set of the instructions to address the remaining target in subsequent iteration. Experimental results on a production project demonstrate that this approach can greatly reduce the total simulation and human effort for functional coverage closure up to 18 times the reduction in CPU hours to increase to 20% PT, 20% point ever coverage to eventually achieve the target coverage closure. Chapter 1 Instruction. As the scale and the complexity of the SoC designs continue to increase, the verification challenge for those designs has been growing exponentially. In particular, SoC interconnect from the backbone of the SoC design make it crucial to thoroughly verify them at early stages of design. However, the complete verification of an SoC interconnect poses a significant challenge due to the connection of the hundreds of masters and slave intellectual property IP cores with the different protocols and the routing of various types of the transactions. A state-of-the-art verification approach involves the scalable universal verification methodology UVM test benches that reflect the interconnected topology, constrained random simulation techniques that generate massive random transactions, and a huge functional coverage model that ensure the thorough verification of the design under duty. And so, consequently, it takes the design verification team an enormous amount of time and the resources to achieve the functional coverage closure by repeatedly running simulation after manually changing constraints in the test bench to target the uncovered areas. This paper proposed a novel methodology to effectively reduce the time and the cost for functional coverage closure in SoC verification by iteratively applying the artificial intelligence and machine learning solutions that have been packaged as a feature of the SimAI from Cadence design systems. To start with, the design verification team creates a set of the test as usual and specified target scenarios. The verification team initially simulated the set of the tests using Xcelium logic simulators. Then the SimAI analyzes the simulation traces and results in order to generate instructions that guide the simulator to reach the target scenarios efficiently. After the verification team simulated the test with the generated instruction, SimAI evaluates those simulation traces and results to generate a new set of instructions for addressing the remaining targets by learning this flow iteratively, and the verification team can step toward closing the target coverage without manually modifying the test or simulation settings. The contribution of this paper can be summarized as follows. First, it adopts iterative machine learning to efficiently address multiple target scenarios for SoC interconnect verification that are extremely difficult and demanding to address to simulating the original test repeatedly. And two, as we applied to propose approach to a reduction approach to a production project to achieve 100% coverage for two challenging sets of coverage beans, spending 4.92 times and 18.20 times less CPU time than the repeatedly simulating the original set of tests, which could only reach the 96.27% and 79.91% coverage respectively. This is the 3-year one is typical SoC with cascaded interconnects. The chapter 2 is the background and challenges. As an SoC, interconnect is the communication backbone within the SoC that connects multiple subsystems such as processors, for example, CPU and GPU, and application-specific processors, to the memory or I/O interface and preferred devices. It plays a crucial role in managing data flows, optimizing performance, ensuring security, and maintaining the low power consumption of the modern SoCs. The design complexity of the SoC interconnect that increased due to first, the integration of the numerous IP components with the different bus interface protocols, and two, the requirement for high performance and the power efficiency. To meet these demands, today's SoC interconnect typically consists of the cascade of interconnects, including the cache coherence interconnect (CCI) and the network NOC and network on chip NOC and AXI-AHB interconnect, and multiple bridges, as shown in Figure 1. Due to the increasing the number of IP components and various bus interface protocols, scalability has arisen as a critical challenge to the verification of the SoC interconnect. In a single SoC interconnect, hundreds of masters and slave components establish hundreds of thousands of data paths, each of which may transfer data with various attributes such as address, direction, transfer size, and other control or data values defined in the bus interface protocols. The data path types and attributes to be tested are captured in the functional coverage model. The number of target coverage beans, including cover point beans and cross coverage beans, had grown in scale with ever-increasing numbers of masters and slaves. So, the functional coverage methodology for industrial designs has centered around constraint random simulation. For an SoC interconnect and constraint random test generate test transactions between a master and slave in order to validate data correctly routed between the master and design designated slaves according to the design specifications. By simulating the same test numerous times, the design verification team can simulate a huge volume of the random traffic originated from hundreds of masters toward hundreds of slaves at the cost of the increased total simulation time due to the increased complexity. So yet, it still remains challenging to reach the functional coverage closure while repeatedly simulating those constrained random tests. In order to reach a state in a simulation where a target coverage beam can be hit, a certain combination of randomization should have happened toward that state. The required simulation settings and randomized combination are distinct for each coverage beam. In general, a random test possesses opportunities to reach diverse states of the simulation. However, it's tricky to reach every state in an extensive list of states that are associated with the target coverage beams. So on the other hand, a directed test can be written to a target-specific state, nevertheless given the huge coverage models and verification complexity. It's infeasible to generate and simulate a directed test for every coverage beam. So that is Figure 2, an overview of a proposed flow. Hence, the design verification team usually simulated the constraint random test repeatedly to hit as many beams as possible and modified the test bench or simulations test settings to directly target the unhit beams. So rarely they confirm the new hit unhit beams are indeed unreachable and executable, and those beams from the coverage model after a thorough analysis as both the coverage model size and simulation time have increased for SoC Interconnect. It has become extremely difficult to close the coverage and meet the project schedule with conventional verification approach. The Chapter 3 is a proposed approach. The large-scale verification projects typically involve periodically simulating a suite of various constraint random tests called a regression, instead of simulating the same regression repeatedly or modifying the test bench to directly test a few specific cases, as in the conventional approach. The proposed approach is to leverage a software solutions called SimAI to iteratively and automatically generate a new regression based on the simulation result of the previous regression. Here, a newly generated regression consists of the original regression itself and a separate list of instructions for Xcelium logic simulator, while SimAI offers multiple objective functions in generating regressions such as autonomous coverage maximization or bug hunting. The proposed approach uses that generates regressions to realize the user-specific test scenarios efficiently. Figure 2 presents a high-level overview of the proposed iterative flow. Initially, the design verification team develops the regression and produces a target specification. The regression mainly consists of a number of constraint random tests and their random seed counts. The target specification contains a list of target scenarios for SoC interconnect verification. Scenarios can be defined as simulation settings of the individual test and a combination of values of random variables in the test bench that corresponding to the routing paths and transition metrics to be tested, according to the coverage model. That is, a particular scenario occur in simulation, corresponding coverage beams will be hit. This information may be extracted from the coverage models or result and the test bench or simulation traces. In step 1, the verification team simulated the original regression using Xcelium logic simulator. Each random test with a single random seed becomes a single simulation run. In addition to the simulating the test, Xcelium also produces simulation data for our SimAI, simulation traces, state information, and a coverage result. So the trace of the simulation run includes the information about which random variables were randomized to which values at which randomized calls. The status of the run refer to whether the simulation successfully completed or presented an error. For a failed run, the status information includes the error or the failure message. The coverage result a run include a functional and code coverage result. After simulation, the verification team launched SimAI, providing simulation data from the original regression and the target scenario specification. Then a feature of a SimAI performed step 2 to 5 and generate a new regression to the simulated. Step 2, which collects the simulation data of the input regression and stores them after pre-processing. In step 3, SimAI learns from the data collected in step 2 by analyzing the simulation traces. It identified all target scenarios in the input specification have been satisfied by simulation runs in the input regression. A scenario is satisfied by a simulation run if the combination of randomization of each variable to value range specified in the scenarios occurs at least once in the specified simulation setting during the run. SimAI also evaluated the difficulty of satisfying the remaining target scenarios by analyzing the collected data in terms of which random variables appeared in the simulation runs of the regression and how they were randomized. For instance, it is more difficult to satisfy a scenario that specifies a random variable to be randomized to a value that has not been observed in simulation traces. The next figure 3 is the SoC Interconnect test bench. So in step 4, SimAI adjusts the target according to the evaluation result from the step 3. and it decided which target scenarios should be addressed in a new regression. It also decided which of them is really jointly included in individual simulation runs of a new regression by analyzing their relationships such as contradiction and independence. Two target scenarios are said to be contradictory if both require a random variable should be randomized at the same time, but to disjoint value ranges. Each of the contradiction scenarios requires a separate simulation run to address it. On the other hand, a pair of target scenarios may be satisfied by randomized distinct random variables. Such target scenarios are said to be independent and they are becoming a candidate to be targeted in a single simulation run. SimAI utilizes such a relationship among the target scenarios when constructing a new regression. And step 5 is the SimAI generates a new regression that aims to efficiently simulate the target scenarios selected in step 4. So the generated regression includes all of a subset of the initial regression test. To be specific, it includes a pointer to an initial regression files, for example, the test code and the number of random seeds applied for each test. So in addition, for each simulation run, the generated regression contains such of instruction that guide an Xcelium logic simulator to steer the randomizations so that the specification, possibly multiple, and the target scenarios occur in the run as scheduled in step 4. So once a new regression is generated, the verification team simulates it and starting a new iteration from step 1. Then repeat the process iteratively until all target scenarios are addressed, at which point the functional coverage will be closed. Addressing a large number of the target scenarios in a single simulation run may result in elongated simulation time. However, this override turned out to be a minor compared to a total simulation time required to close the coverage using the conventional approach, as reported in the next section. Chapter 4 is the experimental result. Section 8 target, design and test bench. We applied the proposed approach to the SoC Interconnect design for a state-of-the-art mobile application processor. The target interconnect consists of a multi-layer interconnect such as cache coherence interconnect CCI, NLC, AXI interconnect, and AHB bus battery, and multiple bridges. Hundreds of the masters and nearly 1,000 of slaves are connected to an interconnected, resulting in hundreds of thousands of functional coverage elements. The SoC interconnect verification environment created in the early stage of the SoC design by attaching the elective verification IP VIPs to the target interconnect in place of all master and slave component. Instead of active VIPs that replace the component, passive VIPs can also be attached to monitor signals between the interconnect and the component duties. Figure 3 illustrates an overview of the target test bench comprised of master VIPs to generate random master sequences to SoC connect. Second is slave VIPs that react to the master sequences. And third is the system verified scoreboard SVD VIP that checks the end-to-end coherence and correctness and integrity of data as they pass through the SoC interconnect. And fourth is the functional coverage model. The test bench has been generated by UVM-based approach that facilitated integrated with VIPs and supports seamlessly configuration for given target interconnected topology. Okay, next one is figure 4 is coverage and the total simulation time for category 1. And from the functional coverage model, two categories of the cover group items have been identified, demanding the tremendous amount of human effort, time, and computer resources for a given verification team in the actual project to achieve the coverage closure. B. Category 1. cover item. The first category check the master and slave control signals such as address, data, interaction with respect to elements of the reachability matrix that indicated for each master, and then access several slaves in access several slaves and an unused address in the system. The coverage model contains over 5,500 such covered items, defining about 1 in 20,000 coverage bins in total. Figure 4 shows the simulation result of the traditional and proposed approaches for the category 1. The traditional approach is to simulate the original regression repeatedly. The original regression contains 274 constraint random runs that consumed 1,744 CPU hours in total for the initial simulation to cover 26.74% of the coverage bins in the category 1. And the figure, in each point, a blue filled circle marks the accumulated coverage until the simulation time measures at each new simulation of the regression. Simulating this regression 24 times resulted in 6,576 simulation runs, taking 41,158 CPU hours in total to cover 96.27% of the bins. As one may note from the blue trend line in the figure, the higher the coverage is, the more simulation runs are required to further increase the coverage. This is due to the diminishing margin return. The first 20 iteration, 5,480 runs and 33,751 CPU hours covered 94.84% of bins, and the additional 4 iterations, 1,096 runs and 7,408 CPU hours usually covered only 1.43% of the bins. The proposed approach takes the original regression and its initial simulation result to generate new regression using SimAI. The first regression generated by the SimAI contained 233 individual simulation runs that consumed about 4,600 CPU hours to hit the additional 72.85% of the bins. Although the average simulation time for a run has increased, those runs were guided to address many target scenarios efficiently. As a result, 99.59% of the bins in category 1 were hit after the total simulation time of the 6,340 CPU hours. In the next iteration, SimAI generated a new regression containing 265 individual iteration runs, aiming to address the remaining target scenarios. It took 2,022 CPU hours to simulate this regression and hit all uncovered bins. By simulating 2 AI regressions in addition to the initial original regression, the proposed approach spanned 8,362 CPU hours, 772 simulation runs in total, to cover 100% of the target bins. This trajectory is marked in Figure 4 by the orange trend line that branches out from the point that represented the initial simulation result of the original regression. In summary, the proposed approach achieved both 4.92 times reduction in CPU time for simulation and 3.73% point increase from 692.27% to 100% in coverage than the traditional approach. Moreover, the proposed approach achieved the coverage closure for the category in traditional approach after consuming 41,158 CPU hours for 24 iterations. Given the design verification team would start examining how remaining 4,478 uncovered beans could be hit. As a common practice, in order to hit these beans, we often modify the test and the setting to directly simulate target scenarios to do the diminishing the marginal return of the simulating the same regression repeatedly. This kind of examination of the remaining coverage beans and possibly modification of the test requires human engineers' time. Hence, the total of time and the resources saved the proposed approach is more than the just reduction in simulation time of the regressions. This approach also saves the additional human effort required to close the coverage by traditional approach. Figure 5 is the coverage and total simulation time for category 2. The category 2, C. Cover items in second category check the quality of the service, QoS, the value transmitted from the master to the target points. The objective of these cover items to validate the transaction for all valid QoS values. 496 cover items in this category contain 5,850 coverage beans in total. Figure 5 shows the traditional simulation result of the traditional and the proposed approach for category 2. The traditional approach here is the same that did for category 1 in section B above. The coverage result for category 2 are presented by the blue points in this figure. After the initial simulation of the original regression, that contained 274 constrained random runs, 8.48% of the coverage beans in category 2 were hit the cost of the 1,744 CPU hours in total. So simulating the original regression 24 times result in hitting 79.91% of the beans after spending 41,158 CPU hours, 6,576 simulation runs in total. The proposed approach diverges from the traditional one after the initial simulation of the original regression. In the first iteration, SimAI generated a new regression with 48 individual simulation runs to hit additional 90.19% of the coverage beans in the category 2 at the cost of 451 CPU hours for simulation. The second regression generated the next iteration contained 7 individual simulation runs that turned out to hit all the remaining beans of this category when simulated, spending 67 CPU hours. As marked in the figure 5 by the orange trend line, the trend out from the initial simulation result of the original regression. The proposed approach closed the coverage gap 91.52% in 2 iterations at the additional cost of 570 CPU hours. Overall, this approach spanned 2,261 CPU hours, 329 simulation runs in total, in reach 100% coverage, reducing the simulation time by 18.20 times, and at the same time increasing the coverage by 20.09 percentage point, and from 79.91% to 100% than the traditional approach. Furthermore, the proposed approach completely closes the coverage for this category as well. In the traditional approach, after simulating the original regression 24 times, and the design verification team would either continue simulating it repeatedly to increase the coverage slowly or inspect the 1,175 uncovered beans and modify the regression to directly target each of those beans. And the summary. For the too challenging the set of the coverage item in the production project, the proposed approach has achieved the coverage closure with 4.92 times and 18.20 times the reduction in the simulation time, respectively. On the top of that, it does not require the enormous amount of the human effort to examine and cover the remaining beans as often requires in the traditional approach. Overall, the proposed approach has been demonstrated to significantly reduce time and compute resources and human effort to function coverage closure in SoC interconnect verification. The Chapter 5 is concluding remarks. It's becoming increasingly challenging to complete SoC interconnect verification in the early stages of the design. We have proposed a number of approaches that has the potential to accelerate the verification process by iteratively adjusting and addressing target scenarios with the aid of the machine learning. In the conventional approach, the design verification team repeatedly simulate a set of constrained random tests for many iterations and modified regression as needed in order to directly address uncovered beans. Instead of repeatedly simulating the same regression, the proposed approach leverages a feature of the SimAI to generate a new regression that aims at simulating uncovered target scenarios efficiently based on evaluation results for previous simulation time, simulation data, and the relationship among these scenarios. By applying this approach to the industrial SoC interconnect verification project, we have demonstrated that it can significantly reduce the total time as well as human effort to achieve the functional coverage closure compared to the traditional approach. We note that the effectiveness of proposed approach depends on the completeness and accuracy of the target specification provided by design verification team. While there is no preferred coding size for the coverage model, this approach assumes that a certain combination of randomization and simulation traces will hit the specific coverage beans being concerned. If the target specification is incomplete, that is, it does not include test scenarios necessary to hit specific coverage bean, the proposed approach may not hit the beans even though all the test scenarios of the provided specification are satisfied. Future work includes driving the target specification automatically. There are acknowledgement and the references. Okay, today I read this paper, the functional coverage closure in SoC interconnect verification with iterative machine learning from DVCON2025. Thank you for your time and see you next time.